All right, good morning again, everyone. Today, in our final 2 hours of classes this semester, I'm going to finish chapter 6. And in the final exam, sections 6.1 and 6.2 will be included, but these last two sections will not be included in the final exam. So 6.3 and 6.4 are not included in the final exam. Okay, but we are going to cover them today. It's actually, we're going to just quickly go over them because these counting processes, the binomial process and Poisson process, actually uses what we already know. The only difference is that we keep observing these binomial events in further trials. So I'm going to talk about them when we discuss these two chapters, but that's basically it. And I'm going to go over what we have covered in 6.1 and 6.2 before we finish them. And if there is time after we finish these things, I will be happy to answer your questions from general from any of these topics. Also, the final exam, we plan to make it include topics after chapter 9. Okay, so it will not include, most probably it will not include questions from the first 8 chapters from 1 to 8. Obviously but it's going to cover 5 and 6. What I mean is that it's 2, 3, 4, and then we jump to 8, and then that's it. In the midterm it was like that, if I remember. We are not going to cover chapter 7, which is queuing systems, which is obviously not going to be included in the final. But yeah, the final is going to include topics after the midterm exam. But this is not for certain yet. As soon as it becomes certain, I will make an announcement on OptiClass about the final exam topics. Our final exam is 8th of July. And it will be, the format is going to be very similar to the midterm exam. All right, so last time on Tuesday, I solved an example about the steady state probability, steady state distribution of a Markov chain. So let's remind ourselves what Markov chains are. So we have a finite number of states. It's not. It may still be a Markov chain, and if we are in counting processes, we are going to see the number of states are going to be infinite, but they will still be countable, discrete. Okay, so we will have discrete state, maybe infinitely many states. It's also possible in counting processes. But when we talk about the steady state distribution, we will usually look at Markov chains which are homogeneous, and also they have finite number of states. Okay, so a Markov chain was a discrete time, discrete state Markov process. So we have time steps that we can keep track of one by one. At time 0, usually time may start at time 1, time point 1, but it usually starts at step 0 to indicate that's the initial state. The initial state is usually indicated as the initial state distribution is usually indicated as P0. One thing that is, in terms of terminology, the book uses the capital P, may be confused with no subscript. The capital P is going to indicate the one step state transition probabilities, that matrix with PIJs. These are this other P. I wanted to write a small p like this, which indicates one step transition probability from state I to state J. In a homogeneous Markov chain, these PIJs are constant for any one step between any t to t plus 1. Okay, that's what the homogeneous property was. The state transition probabilities do not change whether you are at step 500 or 1000. It's always between 2 consecutive time points. If this probability is fixed, then this should be given to you in question. This may not be the case for every Markov chain. For example, it may differ if you're tracking a stock share. For example, depending on whether the current time is Friday, it may the transition from Friday to Saturday may be different than the transition from Tuesday to Wednesday, because the transition in 2 consecutive weekdays may be different on the weekends, especially in these stock prices. Okay, so in that case, we cannot describe the transition from one price to the other. By the way, the stock example that I gave you, it's not discrete state. The price itself is continuous. So it's not a Markov chain. The states are not discrete, but I just wanted to give you as an example. The transition from one price to another, that probability will be different depending on where you are currently in the week. In that case, we cannot have a single matrix that shows all these transition probabilities. In that case, we don't have a homogeneous Markov chain. Okay, so I just wanted to give you an example of a non-homogeneous Markov chain where we are at which time point we are currently may change these probabilities. But if it doesn't change, if in the question is given to you that from one day to the other, if a generic statement is given between 2 days, and then you can assume that the Markov chain is homogeneous and there's a single one-step transition probability between time point to time point. Okay, and we make this assumption. Sometimes the nature of the problem, even the nature of the problem is not like that. Sometimes we make these assumptions to make the problem simpler. These assumptions are made in many places. And for example, in molecular biology, going from one DNA position to the other, we make this assumption that it doesn't matter where you are in the DNA. But in reality, it may matter. Okay, in reality, the problem may not provide you a homogeneous Markov chain, but before you solve the problem, since modeling the different probabilities in different parts of the DNA would be really difficult to do, before you attempt the problem, you make the assumption yourself, saying that I assume that transitioning from this nucleotide to this nucleotide on the somewhere in anywhere on the DNA is same. Okay, when you make that assumption, obviously you're making some small errors, but you do it at the benefit of to model something that is doable. Okay, feasible. So to find a feasible solution, you may have to make such assumptions sometimes. Okay. All right. So here we have a random variable that we monitor in a Markov chain. It may be the weather condition. It may be the grades you take, or the count, the number of scores, the number of goals scored in a game. So whatever it is, this is a single variable, a numeric random variable that we keep track of. And at a fixed time point, it becomes our regular random variable. So we talked about these transition probabilities. And here is the superscript that we introduced here, the H-step transition probability, which means that in these discrete time steps, H time time points after T, the probability that we are going to be at state J, if given that we were at state I at time point T. So this becomes this is called the H-step transition probability. And this can be found by, if you know the one-step transition probabilities, you can always compute this analytically. And one way to do it is to take the successive powers of your state transition. So this matrix, the one-step transition probabilities, if you take the second power of this matrix, it will give you the two-step transition probabilities. The third power of this matrix is an n by m matrix, so you can multiply this n by m matrix with itself. This is how the successive powers of this matrix is computed, by multiplying this n by m matrix with itself. So if you take the h power of this matrix, the values in that h power p to the h gives you the H state transition probability from I to J. Okay, so these matrix powers have really interesting properties. I'm going to, I'm going to just give you a slightly off the topic information about the matrix power. Just a side note. If this matrix was not transition probability matrix, but it was an adjacency matrix of an undirected, unweighted graph. Okay, in an undirected, did I tell you this before? Maybe I like this property so much. Maybe I have told you this before. I'm not sure. So can you write yes or no? Did I talk about this undirected graphs with adjacency matrix representation? Do you remember? Taking the kth power of this matrix, what does it give you in an adjacency matrix? Okay, I mean, if you don't remember, that's good. It will not be a second. Okay, so probably I didn't talk about this before. Okay, so it's good. So, so if you have a graph like this, okay, and nodes represent, you have nodes and there are undirected edges between them. Okay, this may be a very large graph. Okay, you may have a graph like this, thousands of nodes, maybe millions of edges. One way to represent this graph is by having, if you have n nodes, if the number of vertices is equal to n, you may have an n by n matrix where each entry shows whether there's an edge between I and j. If there's an edge between I and j, it's 1. If there is no edge between I and j, we have a 0. Okay, so in sparse matrices, there are lots of zeros on this in this matrix. But so this is the adjacency matrix representation of a graph. Now, there's a really nice property that I like. If you take the kth power of this adjacency matrix, the entries will no longer be 0 or 1. You can have arbitrary non-zero integer entities, like some entry between I and j may be 5. Okay, and this is something really nice. The kth power of this matrix shows exactly how many different paths are there between I and j of length exactly k. For example, if you have a node here, I, if you have a node j here, for example, there's a path here, there's another path here, there's another path here, there are 3 paths. So how many paths are there between I and j? So some of them is, for example, this one is length 2. So how many edges each of these simple paths have? For example, this one has 2 edges, this one has 3 edges. I had another one like this there. So this one has 3 edges. So if there are 3 paths, 3 simple, actually there's another path of 3, 1, 2, 3, there's another path between I and j. So the kth power of this adjacency matrix counts, and the value here in the ijth entry shows how many different paths between I and j of length k. Okay, so this makes sense for k when k is equal to 1. Okay, a path of length 1 between 2 nodes is basically a single edge. We had ones, right? I mean, if there's an edge between them, there's one path between them. If there's no edge between them, there's no path between them. So if you take the kth power, you accumulate all these long-term relationships between these edges will be computed by taking the kth power of this. And the kth power of the adjacency matrix, as I said, just write this. I mean, this is not about statistics or probability. It's more about like algorithms maybe. The kth power of this adjacency matrix, the value here gives you the number of paths between I and j. Right? So let's go back to statistics and probability, where we take the powers of the transition probability matrix. So it's when you take the kth power here, similarly, I mean, I think we may still relate what we do by taking the powers of this. When you take the hth power, it gives you Yeah, actually, it's really related. I just realized that I told you that this is not related. The number of different paths you can go between I and J. It's actually when you take the H power as this transition probability matrix. What is the probability to go from state I to J? What we did, if you remember, from that rainy sunny, we computed all the probabilities from, for example, first day sunny, then rainy, then sunny, for example. We computed all possible combinations of this from to go from a sunny to rainy day. And of those individual paths, the probabilities of those individual paths, we added them up to find the overall probability to go from sunny to 3 days from now, whether it's going to be rainy or not. It's exactly the sum of those paths on the on the state transitions gives you the total probability to go from state I to state J. It's exactly actually taking the H power of this transition probability matrix. The only difference is that we don't have zeros and ones, but we have probabilities. And here, when you take the K power, you're adding up those probabilities. So here it's actually multiplied. For example, to go from state I to state J, if you follow certain transitions, to go from state I to state J, the probability of the path is the multiplication of the probabilities alongside. Okay, so it's 1 1 1. If there's a path, it will be 1 1 1. We will just take it as 1, but it will be the probability to go from state I to state J by following a specific path. That probability will be the product of probabilities of these edges to transition, if these are the individual states. And the probability to go from state I to state J in exactly H time steps, you need to have a path between I and J with exactly H edges. And all these different paths that exist between I and J with length H give you all the possible ways you can go from I to J in H steps. So you have to find the path probabilities by taking as the product of those probabilities, and you have to add them up. And adding them up is very similar to counting how many different paths between I and J exist. If all these transition probabilities were one, and we would have exactly the same thing in this graph theoretic problem we had, number of paths between I and J. And the idea behind this taking the power, H power of this matrix is exactly the same actually. It wasn't unrelated at all, okay? So, so this is, again, don't forget this, if we have a superscript in parentheses, it means this refers to a matrix. This refers to a matrix of transition probabilities, which shows you H step transition probabilities. If you have a subscript, if, for example, you have something like this, it means this is an n by n matrix if you have n states, but this is a 1 by n row matrix, okay, or it's just like a vector. This PT here that you see, when it's subscripted, it becomes the state distribution, okay, the state distribution at time H when we have a subscript in this capital P. And maybe another distinction, it may be italic and the other one is not italic. Let's see. Yeah, it's also italic. No, that's not a distinction. The only distinction between whether it's a state distribution or a matrix of transition probabilities is whether you have a subscript or a superscript. So that's, I think, a bad choice by the author of the book. Maybe he had to do that because these are probabilities, whether it's state distribution or whether they are transition, they are probabilities like P. So to indicate a vector of those or a matrix of those probabilities, it's common to use capital letters to indicate vectors or matrices. So therefore, both are indicated by P. Maybe we could have used this capital letter S to indicate the state distribution. I don't know. So here, let's go again step by step. So we talked about h-step transition probability. When it's not dependent on time, we call that homogeneous. I gave examples about that. When we don't have homogeneous Markov chains, it's possible. If it changes from day to day, these transition probabilities, then it's not homogeneous. The state distribution is the probability to be at that state at time t. So it's actually our random variable. The state distribution is not something that you don't know earlier. When we have a random variable, the random variable is something. It's not a scalar. Unlike scalar entities, random variables can have multiple values with certain probabilities. Okay, that's what a random variable is. A state distribution is just a random variable at a fixed time point t. Okay, so it's the probable mass function for this random variable at time t is called the state distribution. So for example, it's 40% rain, 60% sun tomorrow. That's if t is tomorrow, the weather condition, if x is the weather condition tomorrow, our belief in our probable mass function for tomorrow is this 1 by n row matrix or 1 by n vector, which shows 0.4 and 0.6 in it. P0 is the initial state distribution. And if we know the initial state, and if the one-step transition probabilities are given to us for a homogeneous Markov chain, we can compute anything about it. We can compute what will happen in 10 days from now with certain probability distribution, of course. We can compute the steady state distribution that we solved last time as an example. Okay, so these are the things that we can compute the h-step transition probabilities by taking the h power of the transition probability matrix. So you may ask, what is the probability to go from sunny to rainy in 10 steps? That's what the h-step transition probability is. You may ask, what will the weather be like h steps from the initial state? That's the state distribution at time h. And we can also ask the limit. What is the limit of h going to be in the long term? What is the state distribution as the time step goes to infinity? That's called the steady state distribution. So we have mentioned one step, h-step transition probabilities. We have talked about those. The h power of the one-step transition probability gives the h-step transition probability matrix. And I mentioned its relationship with the two paths on graphs. Okay, we are accumulating basically all the different paths between I and j, which are exactly h steps, because the h-step transition probability tells you that, you know, what is the probability to go from I to j in exactly h time steps. Therefore, we have to look for paths of exactly length h. And this h power gives us that. And here is the thing that we do where we put those two different variables. Here, what we see, let me annotate here. This one here, P0, is a 1 by n row matrix, which shows the state distribution at time 0. For example, it could be something like this, 0.1, 0.9, if there are two states, indicating 10% of rain, 90% of sun, 0.9 probability sun. We would indicate it like this. And this p to the h will be an n by n matrix. This time it will be a 2 by 2 matrix, okay, which shows you what is the probability to go from rainy to rainy and then rainy to sunny. All these will be written here. Let's call it x, y, z, w. Okay, a 2 by 2 matrix. And if you multiply a 1 by n with an m by n, the result p to the h, as you can see, is going to be 1 by n row matrix or 1 by n vector or a row vector. It will indicate the state distribution at time h. Okay, so this is how we compute these things. The transition probability matrices are always row normalized. The sum of probabilities in a row is 1. The state distributions themselves are always also, they're also probability mass functions. They also add up to 1. And the steady state distribution, which we did last time, was the solution to this equation. So it's if we're at a certain time point where the state distribution is given as this row matrix pi, you multiply it with the state with one step. So where you're going to be at t plus 1, you multiply it with this one-step transition probabilities, and you see that you're still at pi. So if it's like that, this pi is not going to change anymore. So you multiply it again with p, it's again going to be pi multiplied. So it's after a certain time point, you're going to be stuck so it's going to converge. Your state distribution is going to converge to something. That's why it's called steady. Steady means not moving, not changing, okay? So steady state means that after a certain time point, you will be stuck at that point after h or h plus 1, 2 steps. It's not going to change. So we may sometimes, in some problems, we may be interested in those steady state distributions. For example, the initial Google PageRank was computed as a steady state distribution to actually, again, random walks on graphs. It's very related to these two. You have some initial state, which imagine we are simulating a random surfer who is surfing the web. And this person is likely to start at any web page randomly available in the world. So that's initial distribution P0. For example, you may have something like this. Let me annotate. Your P0 may be a row vector like this, which contains, for example, if there are 10 billion web pages in the world, each entry here may be 1 over 10 billion, 1 over 10 billion, 1 over 10 billion. Okay, now imagine we have such an initial distribution, which means that this random surfer is really equally likely to start at any web page in the world, because we don't know web pages importance values yet. The Google PageRank, its goal was to compute an importance for a web page by proportional to the links that are linked to that. For example, if many web pages link to it, it should be an important page, right? And it was computed by a very similar Markov process that is like this, which is random walks on graphs, or Markov chains actually. When you are, so here it was like this, the probability to be at a web page at t plus 1, where you're going to be at t plus 1 is given that you are at some specific web page at time t. In this simulation, the random surfer is modeled like this. With some probability, you are going to go to, if given that you are currently at page W, and the next time step, you may go to a web page that contains a hyperlink from the current page you're in. Okay, so you may have transition probabilities from this web page to other web pages based on the links contained in that page. All the other transitions may be 0. If you do it like this, obviously there may be certain islands in the web page connectivity graph, which will have your random walker stuck in some. But we are studying, since actually we are not going to stuck in certain places. We equally likely start random surfing from all over the web. But in order to make this simulation more realistic, they also added a component to Google PageRank to indicate that, okay, at every time step, with some probability, we jump to the next page linked from this, and with some other probability, let's call it 1 minus c, we just continue with a completely random web page. So it's like at every time step, you have two choices with certain probability. You either follow a link on that current page, or you randomly jump to another web page. Okay, so this is how they modeled this Markov chain. And what is the page rank of a web page? The page rank of a web page is the steady state probability. When this random surfer surfs the web until infinity, we ask ourselves, what is the probability that the surfer will be at this specific web page I, at time infinity? Okay, so the steady state probability distribution at time infinity of this web page actually is an indicator about the importance of that web page. If there are lots of web pages linking to a certain web page, its steady state distribution is going to be likely to be larger because at time infinity, since it's visited more, you will probably find yourself more likely in that web page compared to the others. Okay, so this normalized Google PageRank here, it was the initial way how they implemented this. The steady state distribution is something that made our searches really nice in the beginning of 2000s, and this is how Google became a successful company, by making use of the steady state distribution of web connectivity links and the steady state distribution of web pages. All right, so and in these large graphs, when you have 10 million web pages, and solving this equation may be a really difficult thing to do. Here in the book, the example shows this solution could be find by solving a system of linear equations. But another solution that I mentioned earlier to you is to make use of simulation. You simulate starting at some random p0 in which all the states may be equally likely. You may multiply your p0 with, pi0 with your one-step transition probabilities and keep continuing. Let's call it actually not pi0. It should really be called p0 here because pi is the term you use for the steady state. So you start at state distribution at 0. You multiply it with 1. With the p matrix, you find p1. You continue doing this. You find p2 in a while loop. You keep multiplying the previous state distribution with p. You find the next distribution. You keep doing this, and at some point, okay, pt plus 1 is equal to pt times p. At some point, this pt and pt plus 1 are going to be very close to each other. They're going to be maybe they will not be able to distinguish them with up to 6 points after 6 digits after the decimal point. In that case, you may take this as your steady state distribution after the pt values that you compute. If they converge to some vector, you may stop at that point and call it as your steady state distribution. All right, so that's another way to find the steady state distribution. And another thing about the steady state distribution is that the h-step transition probabilities, it contains the steady state distribution as well. So let's try to understand this. So every row becomes exactly the steady state distribution. So let's see how it works out. So what it's saying is that if you have the steady state distribution pi1, pi2, pi3, and pi n for n states, the h-step transition probabilities, for example, if you where are you going to be in h-step when h goes to infinity? In H step, you should still be, I mean, even if you multiply it with your original P, you should still remain at that. But where you're going to be in H steps, let's also try to figure that out. Pi 1, pi 2, and pi n. The first column is all pi 1. Okay, so if you multiply this, you're going to see that the result, let's look at the first entry of the result. Okay, here. It should be pi 1, right? Is it like that? Let's see. Well, actually, it doesn't seem to be like pi 1. It's like pi 1 times pi 1 plus pi 1 times pi 2 plus pi 1 times pi 3 all the way pi 1 times pi n. So is this equal to pi 1? It should be, right? And it's, yes, it is equal to pi 1. Why? If you take this entire thing in pi 1's parentheses, it becomes pi 1 multiplied by pi 1 plus pi 2 plus all the way to pi n. If this is a state distribution, what should be the summation? It should be exactly 1, right? If it's 1, 1 times pi 1 is pi 1. So this multiplication also shows that even in H steps, if you're currently in this state, you're going to be there. All right. Also, if whatever your initial distribution is, so it's also interesting. Wow. So this matrix, when H goes to infinity in the steady state, if it's like this, it's also something interesting. It doesn't matter what these are. You can multiply. They could be anything. For example, 0.4, 0.1, 0. Whatever. Okay, so start with any, give any row matrix like this with any values. It may be all 0.1, 0.1, 0.1. Okay, look at the look at what we do. It's again pi 1 times pi 1 times pi 1 times something, whatever they are. They may be 0.1, 0.1, 0.1. As long as, if this is a valid state distribution, any valid state distribution, the summation of the entries here are going to be 1. So they could be anything. They don't need to be pi 1. As long as their summation is 1, we're always going to get pi 1. Okay? Your second entry will always be pi 2, whatever these are. So whatever state you start from, if you multiply them with this spatial matrix, which shows you the H step transition probabilities when H goes to infinity, they will give you the steady state. And the final thing we are going to talk about here is before we go to section 6.3 is the existence of a steady state. In certain state transitions like this one that I mentioned, again, I gave this example earlier. If you're at state this one, you go to the other state. If you're at this state, you go to the other state. So if you have a state transition in which there are two states and you go to the other state at every state. And there are other examples of transitions where we have no steady state as well. It is possible. So if you look at the H state transition probabilities, for odd number of H, it will be like this. For even H values, it will be like this. So it will never converge. So there is no steady state. The reason is that for any value of H, you see there is a 0 here. This makes this a non-regular Markov chain. So if we have a non-regular Markov chain, steady states may not exist. We may not talk about steady states at time infinity. But here is the definition of a regular Markov chain. A Markov chain is regular if there exists some H in which all the H step transition probabilities between every state are strictly greater than 0. So if for some power of your P matrix, if you have a P matrix and for some H power of your P matrix, all the ij values in that, all the cells for all ij, this pij is strictly greater than 0, then such a Markov chain is called a regular Markov chain, and regular Markov chains they always have steady states. Okay, the steady states exist for regular Markov chains. So this is the second bullet. Any regular Markov chain has a steady state distribution. Now, let's look at this example 6.15 before we go into break. The one-step transition matrix contains zeros. So can we say when there are zeros, is it going to be non-regular? The answer is no. So I mean, it's not going to be non-regular. It may be irregular. So can the Markov chain be regular with zero transition probabilities in it? It can still be regular if you look at this H-step transition matrix. Okay, the regularity is not by just checking one-step transition probabilities. At some H step, if it contains values all greater than 0, then it will be regular. But it may be difficult. You may ask here, how do we know what this H is going to be? Up until what step we should check whether there are non-zero entries? Yeah, this may be, especially if you have very large graphs, this may be difficult to figure out. But usually, I think it may be related to the diameter of your, yeah, exactly, we can simulate. And the simulation does not probably have to go too long. You can go 1, 2, 3, 4, 5 steps. Can you prove that, for example, if I give you the longest path that exists in the state transition graph? Okay, we have many states, so the state transitions are indicated as paths between two states, right? So let me use GIMP here for that. Get a new one. Okay, what I'm asking is, even if you have many states, so state transition, one-step state transition from this I and j is 0, as you can see, if there's no single path between them. But if we have, first of all, we have to, does it have to be connected? No, it may still be disconnected. There may be two connected components different. I mean, going from all states to all state. Oh, actually, it has to be connected, right? If you have a disconnected graph, your transition probability graph, what does it tell you if you have a disconnected graph? It tells you that if you have an I here and if you have a J here, for all H, Pij is 0. Like, you can simply prove that, right? If you have a disconnected transition probability graph like this, is it possible to ever go from I to a J here in some? So this H-step transition probabilities, you can also think about it like this: the existence of a path of length H between I and J. Is there a path between I and J which contains exactly H edges? Okay, and this may not be a simple path because you may have paths. For example, I can go to I and J. We can have a non-simple path in which we visit the same edge between I and J over and over again. Still, it means it will indicate H step transition between I and J. So it includes all non-simple paths too. But if there are no paths between I and J, if the graph is not connected like this, whether simple or not simple, you cannot have any path between I and J. Therefore, H-step transition probabilities are going to be 0, which means this is not going to be regular. All right. But even if it is connected, okay, it may be connected, but there may be certain type of nodes in our graph which which will make it a non-regular Markov chain. For example, if by the way, this graph is a directed graph. Every transition here is directed. Imagine we have a node here, which I'm going to call a CENG node, which doesn't have any outgoing, or it's something like this. It has a self transition of 1.0. So if you come to this node J in H steps, you will, in step H plus 1, you will still be in this state. Actually, it's like a steady state at that point. It will all be here, but the Markov chain is not going to be regular. Okay, so what we have here is that when a Markov chain is regular, it always has a steady state, but the vice versa, this is not an if and only if thing. I mean, if it has a steady state, can we say the Markov chain is regular? Not necessarily. So there may be a Markov chain with a steady state, but the Markov chain may still be non-regular. If we have CENG nodes like this, for example, its steady state may be something like this. When you come to this node, you're going to remain at that node. This may be its steady state 1000. You are stuck with this node. You don't go to. It's impossible to be in any nodes at time infinity if you have a CENG node like this. But yeah, let's go back to our previous question. If we want, our goal was to figure out whether a Markov chain is regular or not. We want to simulate. By simulation, we want to find regularity. But the question is how long your simulation have to continue, up until which age you have to continue your simulation to figure out whether it is regular or not. And my claim was that if you find the diameter of this graph, the longest path between any two nodes, if somebody gives you the diameter of this graph, which is given by the longest path between two nodes, okay, between any two nodes, if the longest path between two nodes is D, I think in these steps you have to, in these steps of simulation, you have to come at some transition probability matrix between 1 and D steps. Your matrix should show all non-zero entries in order to be regular. So this is something that is not written in the book, but I just wanted to bring up as a discussion. The book just says if there exists some H in which this is the distribution, H step transition probabilities are non-zero, all greater than 0, then it's regular. So if you look at this 6.15 right here, 11, 15, this was 14, this is, yeah, I think, yeah, this one is also 6.15 is right here. Look at this, lots of zeros. 0.9, 0.1, 111. So we start the one-step transition probabilities contain a lot of zeros in it. So at first look, this looks like a non-regular Markov chain. It's probably, you may feel that it's going to probably likely to have all zeros all over in H-step transition probabilities too. But if you look at the six-step transition probability matrix, it's like this. And in 6 steps, you can see that it has non-zero, all strictly greater than 0 values. So it is a regular Markov chain. Yeah. So does it talk about, yeah, we only need to verify that they're all positive for some H, but how with what this H is going to be for big graphs, can this H be large? My intuition is it should be related to the longest path on the graph. Okay, but it may not be. I may also think about some cases where it may not be true, but yeah, I'm not sure. Yeah, so it's here. You may also take a look at that. I talk sync nodes. They are also called absorbing nodes. When we have an absorbing node in which after a certain time point there will be no route from state 4 anymore. The age state, it's limit. So it has a steady state. There's an absorbing state. Therefore, after a certain age, the transition probabilities are going to have zero transition from state 4 to other ones. It will be impossible to transition from them. So it has a steady state, but it is still irregular. Okay. This is not a regular, so it's not an if and only if condition. We may have a steady state distribution, but we may still have an irregular Markov chain, but due to these absorbing or sync states, which if you think about these probabilities as energies, it collects all the energy on itself and not giving out to anybody else. So, all right, so this concludes 6.1 and 6.2. So the final exam is going to include topics up until this point. All right. Do you have any questions? All right, so let's have a 10-minute break now. I will stop recording. And at